This is Unit 10, Example 4, Applying the Central Limit Theorem. So in OLI, you'll read about the Central Limit Theorem. It tells you that even if the population distribution is not normal, the shape of the sampling distribution will be a normal distribution when the sample size is large enough. So we're asked between these two graphs to decide which graph is the population distribution and which graph is the sampling distribution, and to explain our reasoning. The graph on the left with the right skew or right tail is the population distribution. It has a spread of about 3, and the center is right here around 1 or 0.75. The graph on the right is the sampling distribution. The sampling distribution has an approximately normal distribution, and this graph is approximately normal. Over here on the right, there's not a clear skew and it looks roughly symmetric. So the sampling distribution graph comes about when we draw a random sample from the distribution. So I come over here and maybe I take a random sample of 30 values from this distribution. I calculate the average of those 30 values that I randomly selected, and then plot them over here in the sampling distribution histogram. And then we repeat again. We take a new random sample of 30 values, take their average, and plot their average in this histogram of the sampling distribution. So the central limit theorem tells us that when the sample size n is large, the sampling distribution of the sample mean is approximately the normal distribution. This is true even if the entire population distribution is not a normal distribution, such as what we see over here where we've got the right tail. So remember, the sampling distribution is a graph of means. So when we pull the 30 values out of here, we take their mean, their average, and plot the average over in the sampling distribution graph. So now that we're working with quantitative data, we're going to set up hypothesis tests to test claims about the population mean, because that's our quantitative value that we're investigating. Previously with categorical data, we looked at proportions, so now we're moving into looking at means, and so our hypotheses will be all about testing the means. So example 5 tells us heights of people the same gender and similar in age are approximately normal. You know from government data that the mean height of young men is 69.5 inches, and standard deviation of the heights of young men is about 2.8 inches. You can assume they're talking about American men. You conduct a survey measuring the heights of 250 male students at LMC, and the sample mean height is 70 inches. You're fairly sure that the mean height of male students at LMC is greater than the mean height of all young men. Carry out a hypothesis test for this claim, and since we have data about the population, this type of hypothesis test is known as a one-sample z-test. So step 1 is to state the claim. And the claim is that the mean heights of male students at LMC is greater than the mean height of all young men. This claim will correspond with the alternative hypothesis. The null hypothesis will assume the mean height of male students at LMC is equal to the mean height of all young men. Remember, the null hypothesis always has equality. So we can write our hypotheses, and here we're assuming the mu sub 0, that if you type it in the TI calculator, they ask for mu sub 0, that's the population value we're comparing to, is 69.5 inches, and then our x bar is 70 inches. There should be a bar on that x. So our null hypothesis, h0, is that the mean equals 69.5 inches, and our alternative is that the mean is greater than 69.5 inches. And this mean that we're talking about is the mean height of LMC male students. So now we want to use technology. You can use a graphing calculator, StatCrunch, to find the z-score to tell us how many standard deviations and the corresponding p-value. So if you're on the graphing calculator, you can go to Stat, Tests, and choose test number 1, the z-test. And we're using that because we know the population data, and you should get these results. Let's go into StatCrunch, and we'll see we get the same results. So in StatCrunch, we choose Stat, and then z-stats, and one sample, and then we know the mean and the standard deviation, so we say with summary. So our sample mean is the 70 inches that we surveyed at LMC students. The standard deviation is the population standard deviation, that's the 2.8 inches. And the sample size was 250 male LMC students. We're going to perform a hypothesis test, and the population mean we're comparing to is 69.5 inches. And then our alternative is that we think that the LMC mean is greater than 69.5 inches. And then I like to check right here under optional graph the p-value plot. So we can go ahead and compute and make our window a little bit bigger to see everything. So we're told the z-stat is right around 2.82, so that's more than 2 standard deviations, so we're thinking that's unusual. And the p-value is 0.0024, so that's less than 5%, so we're thinking these are significantly greater results. These also correspond to the same values we get on the TI calculator. And then because we checked p-plot, if you click the arrow over at the bottom of the box, we see here's our normal distribution, and it tells us that we are 2.85 standard deviations out, and the little red area over here is the 0.0024 proportion greater than our value. So we can visualize that the results are unusual. They're more than 2 standard deviations out. So now we want to state our conclusion. And so the p-value is small, less than 5% or 0.05. Remember, by default, we use 0.05 to make decisions. So we say there is enough evidence to reject the null hypothesis. The sample does support the claim that the mean height of male LMC students is greater than all young men. Now remember, we're saying the sample supports the claim. We're not saying for certain that the claim is true, but we can say it seems likely from the data that the claim is true. So in Unit 9, we wrote hypotheses tests for 2 proportions. Now we are working with quantitative data, so we will see the same steps for hypothesis tests for 2 means. So recently I read a book about garbage called Garbology, Our Dirty Love Affair with Trash by Edward Humes. And in the book, Humes describes just how much Americans throw away and how long it takes trash and dumps to decompose, if it decomposes at all. In the book, the reader learns that Americans throw away lots of clothes, which are slow to decompose, especially synthetic fabrics such as polyester. A researcher wanting to know if synthetic polyester fabric decays significantly different than natural fabric buried 12 strips of polyester fabric and 14 strips of cotton fabric in a landfill for 6 months. The mean amount of polyester fabric remaining was 0.92, and according to fabric manufacturers, the standard deviation for all polyester fabric is 0.03. The mean amount of cotton fabric remaining was 0.87, and according to fabric manufacturers, the standard deviation for all cotton fabric is 0.043. So we're going to carry out a hypothesis test for this claim. And again, we know data about the population, so this hypothesis test is a 2-sample z-test. So the claim is saying that there is a difference between the decay of synthetic polyester fabric and cotton fabric. This will correspond with the alternative hypothesis. And the null hypothesis will assume the decay amounts for the 2 fabrics are equal. Remember, the null hypothesis always has equality. And so down here, oops, I left in some information from the previous question, so we can delete that out. So in here, our null hypothesis is that mean 1 equals mean 2, right? Always equality in the null hypothesis. And then the alternative hypothesis is that mu1 is not equal to mu2, and you can use the not equal symbol. You don't have to write it out like I did. So now on the graphing calculator, you can go to Stat Test and choose test number 3, the 2-sample z-test. And I'm going to go over to StatCrunch and show you how to run it, and we'll see the results are the same. So we'll exit out of our old test we ran. And notice StatCrunch saves your results over here, so you can always click and get your results back. So we'll go to Stat, z-stats again, and now we choose 2-sample with summary because we know the mean and the standard deviation. So for sample 1, the mean was 0.92, so I'm going to let sample 1 be the polyester fabric. And the standard deviation is 0.03. And the size is 12 strips of polyester. Sample 2, we'll let that be cotton. It doesn't matter. You'll just get a positive or negative difference in your z-score if you switch around which group is which. The standard deviation for cotton was 0.043, and the size of cotton was 14 strips. And then our hypothesis test, to say they're equal is always to say that their difference equals 0. So that's the same thing as saying mu1 equals mu2. And then here, our alternative, we just select the not equal to. And then let's choose that optional p-value plot again and compute. And make our window a little bit bigger. And we see these are the same results that we would get on the TI calculator. So our z statistic is 3.47 standard deviations, definitely further out than 2 standard deviations. So it seems as if there's a significant difference. And our p-value is very small, again telling us there's evidence of a significant difference. And if we look at the normal distribution graph over here when we arrow over, we see both the lower values and the upper values, the two tails, are well past 2 standard deviations. And remember, there's 2 tails because we chose not equal to as our alternative hypothesis. If we had changed the alternative hypothesis just to be less than or greater than, then we would only have 1 tail or the other. So now we want to state our conclusion. The p-value is small, less than 5% or 0.05. Remember, by default, we compare to 0.05 unless we're told a different significance level. There is enough evidence to reject the null hypothesis. The sample does support the claim that the synthetic polyester fabric decays significantly different from natural cotton fabric.